In order for two molecules to react, they must first collide. If you watch this video of gaseous water molecules, you can see that the water molecules are moving around in their container, and every once in a while, two of them will collide with one another. And we have a collision, and if that collision has enough energy, then those two molecules have the possibility of reacting. Notice that when we have water molecules in the liquid phase, the molecules are far more close together, and so the collisions occur with a much greater frequency. Let's do a thought experiment to see how we might count the number of collisions that occur in a particular system. To do that, we're going to think about these red molecules, which have a diameter of dA, so these are our A molecules, and these green molecules, which have a diameter of dB. These are going to be our B molecules. If we think about how many times the B molecule is going to collide with an A molecule and try to count the number of collisions, we could imagine thinking about counting those over 1 second of time, and then we would know the number of collisions per second. And that would be a collision rate. If we know the collision rate, then we know how often collisions occur, so we can think about how that influences how often reactions might occur between a B and an A molecule. So let's see if we can count the number of collisions of this B molecule with this A molecule. To do that, we're going to do a thought experiment and think about having this cylinder in our solution of A molecules, and the diameter of this cylinder is going to be equal to the diameter of the B molecule plus the diameter of the A molecule. The reason we're going to do that is because if that's the case, then when my B molecule comes into this cylinder, then if an A molecule is at least halfway in the cylinder, then the B molecule will exactly touch the A molecule and will collide with it. Notice that the B molecule will also collide with any other A molecule that is in the cylinder. So if I can count the number of A molecules in the cylinder, then I can count the number of collisions that have occurred when the B molecule traverses the length of the cylinder. So I'm going to make the length of the cylinder L equal to the distance the B molecule travels in 1 second. So notice that if V in these funny brackets here, so that's going to be the average velocity, if V, the average velocity of this B molecule, has units of length per second. So distance traveled per second. And if I multiply that velocity times 1 second, I will get the distance that this molecule travels in 1 second. So if the length of this cylinder is equal to the distance that this molecule travels in 1 second, which is just its velocity times 1 second, then I can just count the number of A molecules that are in that cylinder, and that will be the number of collisions that this B molecule undergoes with A molecules as it travels through that cylinder. Notice that the radius of this cylinder is 1/2 dAB. If I take the radius squared, 1/2 dAB squared, and multiply by pi, I will get the area of this circle that defines the end of the cylinder. The volume of a cylinder is equal to its cross-sectional area, pi times the radius squared, times its length. And so the volume of this cylinder is pi times the radius of the cylinder, which is dAB over 2, that radius squared, times the length, and we defined the length to be the velocity of the B molecule times 1 second, times time. Finally, if I know the concentration of A molecules, I can multiply by the volume and I will get the number of A molecules in that volume. So if I want to know the number of A molecules, the number of red molecules in this volume, I just need to take the concentration of A, multiply by the volume of the cylinder, and I will get the number of A molecules. That number of A molecules is equal to the number of collisions that this B molecule has undergone with A. So that number of A molecules in this cylinder is the concentration of A times the cross-sectional area. So this area of this cylinder, pi times the radius squared, we're just going to give this symbol sigma sub AB. It's the cross-sectional area of this cylinder times the length of the cylinder, which is the velocity times time. Notice that when I did this, I assumed that all of these A molecules were just stationary. I froze them in place and I let the B molecule move through the cylinder. However, if both the A and the B molecules are in motion, then this velocity is simply the relative velocity between A and B. So at this point, I've counted the number of collisions that one B molecule undergoes with all of the A molecules in the system. But what I really want is how many total collisions. So if each B molecule in my system undergoes this many collisions, then the total number of collisions of all B molecules with all A molecules will be this number times the number of B molecules in the system, because each B molecule undergoes this many collisions. Notice that the units we have here are in terms of moles of collisions that have occurred. The number of B molecules in my system is equal to the number of moles of B molecules times Avogadro's number. And the moles of B molecules in my system are equal to the concentration of B molecules in my system times the volume of my system. So the number of B molecules is the concentration times the volume of my system times Avogadro's number. So if we multiply the moles of collisions of A molecules with one B molecule by the total number of B molecules in our system, then we will have the total number of collisions. It's convenient to do this in terms of total number of moles of collisions per unit volume, because that way we have a variable which doesn't depend on how big my system is. In other words, we have an intensive variable. So the number of moles of collisions per unit volume is equal to the cross-sectional area times the velocity, the average relative velocity of A and B, times time, times Avogadro's number, times the concentration of A, times the concentration of B. This is often called the collision density because it's a number per unit volume, and something per unit volume is typically considered a density. So this is called the collision density. What I really want is not the collision density, but the collision rate. How many times does the collision happen per unit time? So to get this per unit time, I just need to divide both sides of this equation by time. Just bring time over here. Remember, we're doing this for 1 second, so this will be per second. And I will end up with a collision rate that's equal to the cross-sectional area between A and B, the relative velocity between A and B. I've divided by time, so I don't have t anymore. Avogadro's number times the concentration of A times the concentration of B. So this is the collision rate, and it has units of molar per time. Moles per unit volume, so molar per second. The important thing to note about this equation is that the collision rate depends on the product of the concentrations of the two things that are colliding. It also depends on how big they are and how fast they are going.